I'm Minsoo, a research scientist at LGAI Research. Today, I will present UNSPAT, an uncertainty-guided spatiotemporal transformer for 3D human pose and shape estimation on videos. Recent advances in deep learning have made significant progress in single-frame estimation by predicting the SMPL parameters. However, frame-based estimations are limited in that they are prone to suffer from challenging factors such as motion blur and occlusion, which result in temporally unstable prediction. To this end, video-based approaches have been previously proposed. Current video-based studies exploit a rather straightforward extension to the temporal axis, where they first extract static features from each frame individually and then aggregate static features to compose temporal-aware features. The aggregated feature from a specific window of frames is used to predict the sample parameters for a given timestamp. Although this straightforward extension has been shown to improve temporal errors, it results in a significant increase in reconstruction errors. This is mainly because previous works spatially pooled the individual frame into a single feature vector to model temporal relationship with a reasonable level of complexity. In this paper, the main challenge boils down to a simple question. Is it possible to build a 3D human pose and shape estimation framework that takes into account both the spatial and temporal dimensions? At a glance, a spatio-temporal aware framework may seem simple, especially since recent studies have demonstrated the impressive performance of transformer in modeling a relationship across multiple dimensions. However, as the complexity of transformer attention grows quadratically with respect to the input size, extending the input to both the spatial and temporal axes without pooling causes a huge burden in complexity. To address this issue, we propose a simple yet efficient framework, uncertainty-guided spatio-temporal transformer, which efficiently incorporates spatial information in the temporal axis. First, we use an off-the-shelf object tracker to detect the bounding box of a person in the input video sequence and extract features of the bounding box. In contrast to the previous video-based method that used the average pooled vector as feature, we sustain spatial information in the feature. However, as bounding boxes of human regions estimated by the tracker are not spatially well aligned, directly aggregating feature among the temporal domain would lead to suboptimal results. To solve this problem, we propose a spatial alignment module SAM that learns affine transformation parameters to transform each of adjacent frame features to the current frame feature. SAM takes the current frame feature and adjacent frame features as an input and predicts the affine transformation matrix. Given the affine transformation matrix, the adjacent frame features are worked to be aligned with the current frame feature. Then, we aim to encode the sequence of features that are spatially aligned by SAM using a transform architecture. However, since the complexity of the transform attention grows quadratically with respect to its input dimension, computing attention for spatiotemporal feature results in a computational burden. To address this problem, we introduce spaced batch. As the spatial positions for the features in a temporal window have been aligned by SAM, we can decompose the temporal correlations from spatial positions by treating the spatial dimensions as a batch and calculate the tension only between identical spatial positions. This results in a significantly reduced complexity while achieving better performance than considering the full spatiotemporal attention. Also, we propose an uncertainty-guided attention reweighting method. When considering temporal correlation with transformers, it is crucial to prevent the propagation of errors in specific frame to overall sequence prediction. This is especially critical in the case of videos, where challenging factors in certain frames can lead to erroneous output. To address this issue, we propose a novel uncertainty-guided attention reweighting. The key to our attention reweighting is predicting the spatiotemporal positions where the model is highly susceptible to uncertain information. During training, we intentionally create synthetic artifacts by replacing random spatiotemporal positions with those from other video in the training batch. Then, we train a small network to discriminate the artifacts that typically occur in challenging regions. During test time, the uncertainty map predicted by the estimator is used to reweight the attention for the spatiotemporal positions where artifacts might have occurred. In detail, our transformer calculates the spatial attention weights using the input features as key, query, and value. Subsequently, we parallelize the attention with the predicted uncertainty map. We present a visualization of the attention weights and uncertainty map when a synthetic noise patch is added to the frames. The second row shows the predicted uncertainty map, and the third row displays the attention map. As shown in the figure, our uncertainty estimator accurately predicts high uncertainty value for the occluded regions. Furthermore, the predicted uncertainty map is used to reweight the attention map from the third row to the fourth row. The last row displays the predicted 3D mesh when each time sequence is the current time sequence, and the results demonstrate the robustness of our model to occlusion. Compared to other video-based methods, our method shows better performance in terms of reconstruction error and acceleration error, especially in the case of hard occlusion. For quantitative evaluation, we compare the reconstruction and temporal performance of our UNSPAT with those of a previous video-based method. The table shows that our method outperformed previous state-of-the-art method by a large margin on all three datasets. With the result, we demonstrate the effectiveness of our UNSPAT that aggregate spatiotemporal information and prevent error propagation with the proposed uncertainty-guided transformer. Here we analyze our model and recent works that utilize the transform architecture such as MET and MPSNet. MPSNet computes self-attention along the temporal axis with average pooled feature. This approach exhibits low flops and acceleration error, but sacrifices spatial information, leading to poor reconstruction performance. Next, MET completely decomposes the temporal and spatial axis and computes full attention for each axis. This architecture significantly increases complexity when computing attention for the spatial axis. Additionally, this model becomes biased towards spatial information over temporal information. Therefore, MET demonstrates reasonable reconstruction performance but suffers from high computational cost and acceleration error. However, by applying SAM and spaced batch, our model computes temporal attention for each spatial position with reasonable complexity. This approach results in high reconstruction performance and low acceleration error, all while requiring less than 10% of the computational cost of MET. Here is an ablation study. The first row is the straightforward implementation of a spatiotemporal transformer where full attention is calculated. However, despite its exorbitant complexity, this variant shows serious degradation in performance compared to a variant with spaced batch. When you apply spaced batch and SAM module to our model together, the performance increases by a large margin, and the uncertainty-guided attention reweight module shows additional performance gain.